Hi, I'm Anthony.
Hi, I'm Stephen.
And we're here to talk about the application of maximum and minimum. Yes, guys!
On coordination. The local minimum is the lowest y value in the immediate region of the function, and the local maximum is the highest y value in the immediate region of the function.
Even though the local maximum and local minimum are the highest and lowest y points of the immediate region of the function, they're not the highest and lowest y points of the whole function. The highest y point of the whole function is the global maximum, and the lowest y point in the whole function is the global minimum. Okay, now we're going to show you how to find the local minimum, maximum, and points of inflection using this function. Okay, first you want to derive the function by bringing the power down and minusing it by 1 for each of the numerals, and then derive the function again. Okay, now that we have our first derivatives, we have to use them. So we know that stationary points are found at the first derivative equals 0. So we make 0 equal to 5x to the power of 4 minus 45x to the power of 2. And then we factorize it out to 5x squared. And then we go to find our values of x. So we have 5x squared equals 0, and x squared minus 9 equals 0. And this is a perfect square, so we get x minus 3, x plus 3, and then that means x equals 0. This is x equals 3, and x equals minus 3. So now we use these values of x to sub into the original function and to find our y values. So we get a function of 0 equals 0 to the power of 5 minus 15 times 0 to the power of 3, which equals 0. Function of 3 equals 3 to the power of 5 minus 15 times 3 to the power of 3, which equals negative 162. And we have the function of negative 3 equals negative 3 to the power of 5 minus 15 times negative 3 to the power of 3, which equals 162.
By subbing in the x values into the original function, we are able to get the y value for each of the stationary points. But with this y value, we must sub it into the second derivative that we found out in the beginning. So f derivative 2 equals 20, 0, 3, minus 90 to the 0. So that's all 0 because we're basically timesing it all by 0. So f derivative 2 equals 0. And then this one would be f2 equals 20, 3 cubed, minus. So this is just basically, we're just subbing it into the second derivative. Equals 207. So we're basically doing all the calculation for you. Okay, and the last one will be f2, and it's a negative 3 because we got negative 3 as the upper x value. Sorry about this. Skip 3 minus 90, negative 3. Okay, and that's going to equal negative 270. Each of the stationary points, so for the first one, x equals 0. So therefore, it's neither of the maximum or minimum. And for the second one, it's 270. So therefore, x is greater than 0. And therefore, that means it's the minimum. For the second one, for the third one, I'm sorry, fx is less than 0 because it's negative 270. So therefore, that will be our maximum in the graph.
Okay, so this is a graphical representation of the data we've required. We have our stationary points here, here, and here. At this stationary point, the second derivative equals a negative, so it's negative on either side of the stationary point. At this stationary point, the second derivative is positive, so it's positive on the other side of the stationary point. At this stationary point, there is a second derivative of 0, so it goes up on one side and down on the other side of the stationary point. This is also a point of inflection. This is a graph of sea temperatures global from the time of 1982 to 2009. We see a lot of local minimums and local maximums in this function. But then we have our global maximum and our global minimum in this function.